This is our first lecture in the fifth unit. The topic that I will cover in this lecture is perturbation. So, what does perturbation in English means? The word perturbation actually means small change or small disturbance. So, what does perturbation means? Perturbation means some small change or small disturbance. Okay, but in mechanics, perturbation is obviously a small change, but in what quantity? So basically, a small change in Hamiltonian is called as perturbation when we study like the concepts of mechanics. So let that small change be delta H. This H is the Hamiltonian of the system. H naught is the unperturbated Hamiltonian, and this delta H, that is the change in Hamiltonian, is given by delta H, and this is called as the perturbated Hamiltonian. And this H naught is we will consider when there is no perturbation, when there is no perturbation. At that time, the perturbation Hamiltonian would be H naught, and then we will add it by delta H, which is the change in the Hamiltonian, that is the perturbated Hamiltonian. Basically, there are two types of perturbations. The one is time dependent and the other is time independent. It's really simple. If the delta H contains time t, then it becomes time dependent perturbated Hamiltonian. And if it is time independent, for example, delta H cos kx, over here there is no time. That's why this delta H is independent from time. So there are two types of perturbated Hamiltonian, time dependent and time independent. I hope this much knowledge is sufficient. So now what we will do is see these are your notes that I have provided. So it had all the concepts. You can read it properly, but in short, I will explain it to you what is the basic. So see, this is the Hamiltonian, which is like after the perturbation delta H, as I have already told you, delta H is the perturbated Hamiltonian. So Hamiltonian would be H naught plus delta H. This I have already explained. Now we are studying transformations, right? So these coordinates pq will transform to coordinates alpha beta. Obviously you will need some generating function, so this s would be the generating function. You have studied all the cases when the transform coordinates are constant. You know the Hamiltonian vanishes at that time. The both the coordinates become constant. All this we have already done. So, but when I will consider the unperturbated Hamiltonian, all the cases we have already studied. But in the this lecture, or basically in this chapter, we are considering perturbations. That means the Hamiltonian is changing. There is a small change in the Hamiltonian, that is delta H. That is the perturbated Hamiltonian. So basically, what this delta H will change in the entire solutions in the harmonic oscillator problem, every problem we will consider again, but now we will consider that there are small changes in the Hamiltonian. Okay, that is the delta H, it is the perturbated Hamiltonian. So now the new Hamiltonian, when I will consider this Hamiltonian, that is the unperturbated Hamiltonian plus perturbated Hamiltonian, at that time the new Hamiltonian will not vanish and the transformed variables will not be constant. Obviously there will be change, so calculations will change, and we will observe that the new Hamiltonian will not vanish and the transformed variables will not be constant. Okay, so we know that after transformation, the Hamiltonian is denoted by K. This is alpha beta. We know that K is H plus del S by del T, where S is the generating function. Now we will replace H by H naught plus delta H, because now we are considering the case of perturbation. Okay. So up till now, I have already explained. Now what we will actually do in the question is, see, we have equation of motion. Okay, we will find the value of alpha I dot and beta I dot. How will you do it? What you have to do is, sorry, here there is some mistake. Delta H. We have to take here delta H. Differentiation of delta H with respect to Bi with a minus sign will give you alpha I dot. and beta I would be the partial differentiation with respect to alpha I of delta H, this quantity, delta H. So this quantity we will have to find alpha I dot and beta I dot. Obviously, delta H would be a very small change. So alpha and beta are not going to change very rapidly. So we have to find different orders of solutions. So in order to find the first approximation solutions, what we will do, we in this alpha I dot and beta I dot, in the right hand side you have alpha and beta, right? So in these equations, after coming to this point, we will replace alpha and beta by some constant unperturbated values. I know all these things are getting complicated for you, so this would be difficult to understand, but once I will solve one problem or once I will take one theorem, no, at that time you will understand what everything I have written. This is in short to solve the entire problem. So now I will directly go to the theorem, because without theorem you will not understand anything over here. Okay, so see, now I will consider the theorem. Finally, over here, when you will replace the value of alpha and beta, you will get alpha I dot and beta I dot. So this is dot means differentiation with respect to time. In order to find the value of alpha 1 and beta 1, what you will do is you will integrate it with respect to time t. So after integrating, obviously, you will get the values of alpha 1 and beta 1. Similarly, you can obtain this is the first order perturbation. Similarly, you can obtain the second order perturbation alpha 2 and beta 2 and so on. Okay. In this lecture, I will only explain you the first order perturbation. The second order I will discuss in the next lecture. So even if you have not understand much things for now, this theorem will help you understand more things. You should know about what perturbation is, means small change in the Hamiltonian, how it will affect. Previously, the Hamiltonian vanished when the transform coordinates are constant, but in these cases it will not vanish. These are the pictures of your notes. In this I have written because I know the handwriting is not much good. So this is the first question that I will consider. Okay. See, what is the question? By the method of time independent perturbation theory, find the first order solution for a system of a particle of mass m moving in a force free motion in one direction by assuming the initial condition beta naught is 0. This is the question that I will solve in this lecture. See, I have to consider time dependent perturbation. As I have told you, there are two types of perturbations, time dependent and time independent. Time dependent perturbation means in the perturbated Hamiltonian there would be time. Okay, so see, we are considering a system of a particle of mass m, so everything is happening in one dimensional system, and even the degree of freedom is one, and the mass or the object is moving in a force free field. So this concepts are really easy. This question you have already solved entire question, but in the case where there was no perturbation, that means there were no changes in the Hamiltonian. Now we are doing the same question, but now what we are doing is we are considering a small change in perturbation. Okay, so this is how the question will. The first half of the question is similar to what you have solved previously, but still I'll repeat it. Consider one-dimensional system of particles of mass m moving in a force-free field. We are considering a field which is force-free. Okay. So the system has 1 degree of freedom and the generalized coordinate is x. Obviously, in this case, the system has 1 degrees of freedom. So the kinetic energy of the system is given by half mv square. V is the velocity, that is dx by dt, that is the rate of change of displacement. We have considered a generalized coordinate as x. So see here, kinetic energy would be given by half m x dot square. We know that momentum is linear momentum is given by mass into velocity. So m into x dot. I will find the value of x dot, that would be p by m. Then I will replace the value of x dot from here to here. I will get p square upon m square. 1m will get cancelled, and finally I will get the value of the kinetic energy T is equals to 1 by 2m p square. So in this way you have got the kinetic energy. Plus we also know that in a force free field the potential energy is obviously considered to be zero, right? So our potential energy would be zero. One second. So our potential energy is zero. So thus the Hamiltonian H naught is given by, you know that the Hamiltonian is equal to total energy plus kinetic energy in a force free field. So here the kinetic energy is given by this, potential energy is given by this. We will add both the quantities and we will get the Hamiltonian H naught, which is H naught is equals to 1 by 2m p square. This is equation number 1. Okay. Up till here we have just found the value of Hamiltonian. See which is the wait a second, which is the perturbated Hamiltonian. Okay, in this we have considered the sorry, not we have not considering any kind of perturbation in the first cases. So since H is independent of X, see here, we have done this already in the previous lectures. I have explained everything to you very clearly in the offline lectures. H naught is 1 upon 2m p square. This quantity is independent of X. If the Hamiltonian does not contain the coordinate, then that coordinate is said to be cyclic. So here Hamiltonian does not contain H. So obviously our the coordinate x would be cyclic. Hence, the corresponding momentum is considered to be conserved. We have seen that if the coordinate, like the position coordinate, is cyclic, then the momentum is conserved. That is, the momentum is constant. So here the position coordinate is cyclic, hence the momentum is conserved. That is p is equals to alpha for suppose. I hope everything is clear. Then this is the Hamiltonian Jacobi equation. You everybody, I know you already know the Hamiltonian Jacobi equation. This also we have done in the previous lecture. So this is the Hamiltonian Jacobi equation. This is the value of h. I will replace the value of h by Hamiltonian Jacobi equation. We know that p is given by del s by del x, where s is the generating function. So here I have the value of Hamiltonian. I will replace p by del s by del x, and I will put the value of h in the Hamiltonian Jacobi equation over here. So the value of h would be 1 by 2m p square, but p is replaced by del s by del x. So 1 upon 2m del s by del x square plus del s by del t equals to 0. This is equation number 2. Also, you must remember everything. Since this Hamiltonian Jacobi equation, the terms having x and the terms having t are separate, the solution would also be in the separable form. So the solution S, which is a function of x and t, okay, can be written in the form of w of x plus t of t in the variable separable form. This this term will only consider the x terms, and this term will only consider the t terms. Okay, so what I will do, I will use the equation number 3 in equation number 2. That is, when this term I will consider, here there would be differentiation is with respect to x. So I will replace s by w of x, because the other quantities would obviously be 0. So we know that S is written by W plus T. Here W is a function of X and T is a function of T. When I will differentiate partially with respect to X, at that time the differentiation with respect to T would be 0. So we will differentiate this quantity with respect to X, and this will be equal to differentiating W with respect to X. So here I will replace S by W, and this S would be replaced by T, because the partial differentiation is with respect to time T. I hope everything is clear. So this S would be replaced by W, and this S would be replaced by T, and we are finally here. What I will do is I will take this term over here in the right hand side, and I will come to here. Okay, so here I have already reached C. this quantity over here. So 1 upon 2m del w by del x square plus del t by del t, this quantity I will take over here and I will get these quantities. Okay, now what I will do is I will see this for this side, like for left hand side the right hand side is constant because it will contain only x terms, then these right hand side will contain t terms. So for left hand side right hand side is constant, and for right hand side left hand side is constant. So basically we will equate this to some constant, say alpha square. So all the quantities like the left hand side and right hand side both we will equate by alpha square. So del w by del x square equals to alpha square, and 2m del t by del t is equals to minus alpha square. Now what you will do is, now you will find the value of w. So del w by del x would be alpha after taking square root on both sides. Now you will integrate del w by del x with respect to x in order to find w. So after integrating alpha with respect to x, I will get alpha x. So the value of wx would be alpha x. Similarly, you will find the value of t. In order to find the value of t, take 2m over here. Del t by del t would be minus alpha square upon 2m. Now, in order to find the value of t, you will integrate it with respect to t. So, minus alpha square upon 2m is constant. So, integrating it will give us minus alpha square upon 2m into t. Finally, you have the value of w and you have the value of t. We know that the solution, that is the generalized function s, is given by s of x comma t is equals to w of x plus w of t. We have found the value of w and we have found the value of t. So we will put this in equation number 3 and we will finally get the solution, that is the generating function. So this S would be a generating function. I hope up till here, I think you must be understanding it very well because we have already studied all these previously. This is just a repetition because up till now I have not considered the case of perturbation. These are the cases we are studying without perturbation. So see, we have the value of S, that is the generating function. Now the transform momentum is alpha, we know, and the transform position coordinate is q. So we will replace beta by q. So which would be, since this is the generating function, we know that p is given by del s by del x, but x is alpha. So see, b, the position coordinate, here there is capital P, not small p. By mistake I have written small p. This has to be capital P. So in order to find the value of q, that is beta, it would be del s by del alpha. This also you have done already. So the value of beta from equation number 5 would, we will differentiate it with respect to alpha. After differentiating s with respect to alpha, here there would be alpha and here there would be 2 alpha. This 2 and this 2 will get cancelled, other quantities are constant. So finally, after different partially differentiating it with respect to alpha, you will get the quantity as beta is equals to x minus alpha t by m. This you have got by differentiating equation number 5 partially with respect to x. So, sorry, alpha. So finally you have the value of beta. From here you can find the value of x. X is equals to alpha t by m plus beta. This is equation number 6, and basically this is the solution for the force free motion. We have already done this. X is equals to alpha t upon m plus beta. Now I will shift to the case of perturbation. Up till now I have already solved. I have found the value, or that is I have found the solution for the force free field, that is x is equals to alpha t upon m plus beta. I will use this equation, okay, later on. Now suppose from here things are different, so you need to pay attention. See, now I am considering the case of perturbation. Now the perturbation Hamiltonian, you know, it was given by delta h. So you have to consider delta h, and delta h is given by m omega square x square upon 2. Okay, delta h is given by m omega square x square by 2, where omega is some constant quantity. Where omega is some constant quantity. See here, omega is some constant quantity. So finally you have the value of delta h, which is m omega square x square upon 2, and omega is some constant. So the Hamiltonian would be given by h naught, which is the unperturbated Hamiltonian, plus delta h, which is the perturbated Hamiltonian. H naught we had already found in my previous solutions. H naught was given by 1 upon 2m p square. Just now we had done. See, right now we had find the value of h naught in equation number 1, which is 1 upon 2m p square, and the value of delta h, is given over here. See, the value of delta h also we know. Now only we had written the value of delta h is m omega square x square by 2. So h is given by h naught plus delta h. H naught is the unperturbated Hamiltonian, and delta h is that small disturbance or change in the Hamiltonian, that is the perturbated Hamiltonian, which is given by this quantity. Now taking 1 by 2m constant, finally you will find the Hamiltonian in case of the perturbation. Now with the help of equation number 6, the perturbated Hamiltonian delta h in terms, see, in equation number 6 we had the value of x. See, in equation number 6 we had the value of x. I will put this value in this equation. Yeah, so I will put the value of x in this equation. So finally our equation would be transformed to this quantity after solving everything. So over here in the value of delta h, when you will put x as alpha t upon m plus beta, you will get this equation, and this is the value of delta h. Now we need to find the first order perturbation, that is the value of alpha 1 and alpha 2. What I had written initially, I had a page everything where I had written the procedures. There I had told you that you have to consider alpha dot as minus del delta h by del beta, and beta dot is del delta h by del alpha. So what you have to do is you have to differentiate partially delta h with respect to beta. So it is very simple elementary differentiation. After differentiating it with respect to beta, see, this quantity contains beta, so 2 times into this quantity, this 2 and this 2 will get cancelled, and this would be the value of alpha dot. Alpha dot is obtained by differentiating equation number 9 with partially with respect to beta and taking a minus sign. So in this way you can find the value of alpha dot. Similarly, you can find the value of beta dot. In the same way, you can find the value of beta dot. How can you find beta dot? Differentiate partially equation number 9 with respect to alpha. After differentiating equation number 9 with respect to alpha, see, alpha is here. So 2 times into this quantity, and the constant alpha by m would be multiplied, and finally you will reach to this term. This is the value of beta dot. Now in order to find alpha dot and beta dot, what you have to do is you have to replace alpha and beta by using the initial conditions. One moment. Yeah. So the first order perturbation is obtained by replacing alpha and beta on the right hand side by their unperturbated values alpha naught and beta naught. For simplicity, I will consider the initial conditions. So initially when x is equals to 0, beta is obviously 0, and the initial value of p is alpha naught. So what you have to do, in this equation number 10a and 10b, you have to replace alpha by alpha naught and beta by 0. So after replacing and after finally finding, see, you will get this conditions. Your alpha 1 dot would be equal to minus omega square alpha naught t, and beta 1 dot would be alpha naught omega square t square upon m. Okay, now in order to find the solution, what you have to do is you have to integrate alpha 1 with respect to t and beta 1 with respect to t. After integrating, you will reach here. You'll get the value of alpha 1 and you'll get the value of beta 1. Done. So basically, for the solution of x and p to the first order, what you will do, it is very simple. You will replace the value of alpha 1 and beta 1 in x. Okay. So x would be alpha 1 t by m plus beta 1. Replace alpha 1 by this quantity and beta 1 by this quantity. Finally, you will get the value of x, and the value of p is alpha 1, which is alpha naught 1 minus omega square t square upon 2. So finally, we had completed alpha 1 and beta 1 are the values in case of perturbation, and solution for x and p to the first order is given by this. Here you have find the x, that is the position coordinate, and here you have find the value of the momentum, that is p. We had already found the value of x, which was alpha t by m plus beta, but that was in the case of unperturbated case, right? But here we have considered the perturbated case. In perturbated case, alpha would be replaced by alpha 1 and beta would be replaced by beta 1. And the value of alpha 1 is given by alpha naught minus omega alpha square t square by 2, and beta 1 is alpha naught omega square t cube upon 3m. So after replacing and taking some things common, you will reach here. And the value of p, see here, we had already written that the value of p is alpha naught. So, but now after perturbation, the value of b would be alpha 1. So, alpha 1, the value of alpha 1 is here. We have taken alpha naught common, and this is the final solution of the perturbated case. This is the first order solution. The second order solution I will take in the next lecture.